Welcome back as we next overview the operating principles of a capacitor start induction motor. In this demonstration, we have a very basic model of a single-phase induction motor featuring a main or run winding and a squirrel cage rotor. When AC power is supplied to the stator coils, a pulsating magnetic field is produced between the two pole faces. Notice that the rotor is not self-starting, but oscillates backwards and forwards, since the pulsating magnetic field induces two equal and opposed torques in the rotor. In order to get the rotor to rotate, it is necessary to apply a force to the rotor at right angles to the main field. The applied force has in effect created an imbalance in the torques, and the resulting torque causes the rotor to turn in the direction in which it was started. A more practical way of generating a force or starting torque is to add an auxiliary or start winding and position it at 90 degrees to the main or run winding. Then, by connecting a capacitor in series with the start winding, the current in the start winding will lead the current flowing in the run winding. When the run and the start windings are energized, the rotor self-starts due to the combined effect of the rotating field produced by the two sets of windings. When the rotor reaches 80% of its full speed, the capacitor and start winding can be disconnected. The rotor will continue to turn by the induced magnetic effect of the pulsating magnetic field produced by the run winding. Changing the direction of rotation is possible, when required, simply by changing the direction of the starting torque. To achieve this, we swap the polarity of the start winding without changing the polarity of the run winding. In this state, the run and start windings are energized, and the rotor self-starts in the opposite direction by the action of the two-phase field produced by the run and start windings. After the break, we will apply these basic principles to a typical capacitor start induction motor.